some really pretty cool patterns and software that go along with PixelBlaze. All right, so let's get started. So awesome. I'm all about getting kids to code with PixelBlaze. It's pretty educational. And the nice thing about my favorite thing about PixelBlaze is just the whole interactive nature of and the instant feedback you get. So teaching kids to code, if I do sound pedantic, it's because my experience teaching coding is kids, and I apologize in advance. And teaching kids to code, the beauty of why kids learn faster than adults is they're not afraid to try things and they're not worried things will break. And that's actually generally the right approach because I've tried and haven't broken a PixelBlaze yet. So don't be afraid to try things even if you're not sure what they do. And the downside of teaching kids is that they don't have the patience to compile and test and evaluate, and the iterative cycle seems very long to them. So PixelBlaze's instant feedback in the IDE is a really, really great way. It's a fantastic way to learn and see, how your changes immediately affect the patterns. So, all right. And what's especially nice is just how it simplifies. You can use the same patterns for LED strips that are in 1, 2, or 3 dimensions. So if you see you can see my, am I filling the screen, by the way? Yep,
yeah, we see a camera.
Okay, so you can see here on the table, I've got a couple different demos set up. So I've got an LED strip. This is actually really high density. It's 168 pixels. But just a simple LED strip. I've got the Lux lavalier pendant that I'm wearing, which is a 2-dimensional arrangement of LEDs in a Fibonacci spiral that Jason Kuhn designed and put together and specializes in. If you go to his store, maybe drop his link in the chat, by the way, if anybody wants some very cool 2-dimensional arrays to do LED patterns on. Jason is your really good source. His shop is Evil Genius Labs. Little plug. And then I've got a matrix, 3D matrix. And it's really nice how easy it is to program all of these. And you can use the same patterns on multiple shapes in different dimensions. And you can see, if you see behind me, there's a string art. I've basically taken an LED string and wound it in a circular pattern. And I can run the same patterns in all of these because of the PixelBlaze mapper. So the patterns are separated from the actual, the code for the patterns is separated from the actual physical layout of the pixels. So the pattern fills space, and what colors and intensities the pixels display are basically determined by where they are in space. So the first thing you want to do if you get started, if you have something more complicated than just an LED strip, is to tell the PixelBlaze program where your LEDs are in space. So we'll start with that. All right, I'm going to do a quick transition to, hang on, no, not that, to presenting mode, window, and that should be it. Okay, so let's go to, all right. So is there anybody here who hasn't used a PixelBlaze at all? Just so curious. Wait, I'm not seeing the chat right now, but okay.
Cordelia,
yay!
Yeah.
All right. So if you haven't used, good. So if you haven't used a PixelBlaze at all, anyway, I don't know if you can see everything.
We can see your screen.
You can see my screen? Okay. So, the PixelBlaze is a tiny little controller that looks like this. There's also a smaller version that I don't have out right now. So all you really need to do is provide power and wire your LEDs to the PixelBlaze. And then it actually has its own access point, or that you can, I'm not going to do the getting your PixelBlaze on your Wi-Fi introduction because that's really well documented. Actually, everything is really well documented. I'm just going to try to summarize some of the simpler components. But once you get your PixelBlaze on your Wi-Fi, it serves it hosts and serves a website that comes with a bunch of really great built-in patterns. Right now, I've got a few different PixelBlazes running. This is the page you're seeing is the different pattern options that most of them come built in, but I'll show you how to create your own in a minute. So you can switch. These are the ones that should be showing up on the LED strip right here. I may actually turn off the cube and Lex Leveler for a moment to reduce the distractions. So you can see you can change the different patterns by simply clicking on their names. And you can also edit them, which I'll show you in a minute. But you can also, I wanted to do this with the grid. You can also, if you have something more complicated than LED strip, you can tell the PixelBlaze where your patterns are, where your LEDs are in space using the mapper. So if you look at the top of the PixelBlaze server window, the PixelBlaze window that's being served by the board, you can see the different tabs. The patterns list all the patterns. The editor lets you edit the various patterns. We'll get to that. The mapper isn't showing anything right now because for a one-dimensional LED strip, it doesn't really matter. It assumes they're all, just in a row in space. But it gets more complicated if you want your patterns to look nice on a two-dimensional shape, like this LED string art behind me, or say this matrix, you have to tell it where the pixels are. So we'll start with that. I'm going to start with a simple example. So I'm actually going to unplug this particular PixelBlaze. I don't know if you guys can see this from this LED strip. And I've got this matrix, which is actually 8 vertically and 32 horizontal pixels for a total of 256. If I just plug this in, it'll come up in 1 second. All right, so I've just moved the same PixelBlaze from a strip of 168 pixels to this matrix. And you can kind of see, you can actually see the layout if you go back to the patterns. And this very first pattern, an intro to PixelBlaze code, shows you the layout of the LEDs in the matrix. And I got to change, if you go to the settings, I'm going to change the number of pixels from 168 to 256. And then go back. And it should actually, you notice it's kicked in instantly, that the LED pattern now extends all the way to the end of the matrix. But, that's not super, super interesting. I can still run the same patterns as I was on the LED strip, but it's just going to run them, it's going to assume it's a one-dimensional LED strip and run them in the order in which the pixels are arranged in the matrix. So anything like this is some of these are a two-dimensional pattern won't look, you can't see a two-dimensional pattern in a one-dimensional layout. So let's go back to how you use the mapper right here. So the nice thing is most of the most common scenarios for pixel layouts are actually already in this demo in the examples that Ben has provided. So you can see, for example, if you click on this, if they were arranged in a ring, this is the functionality that would show you the ring. And you get a preview of how a simple rainbow pattern will look on the pixels. So let's go to the matrix. Now, here's what I wanted to show, because I could actually figure out myself where each of these LEDs are in space. And this matrix example isn't going to work exactly right for this layout. It's pretty close, but you can see there's a function. Oh, all right. I've already there's a function in the mapper that actually creates a list of positions of each of the pixels in the matrix and loads them up. So one thing I forgot to mention is that you could actually just put in a set of points to explain where all the LEDs in the matrix are, or you can have, if there's a regular pattern, you can have a function generate them. I'll go back to how you can enter the points in a moment, but this is a function that generates an array of points that tell you where each LED in the matrix is. Now, I was just going to show you how, even if here, let me go back to patterns and pick a different pattern, for example, that only works in a 2D setting. So now this layout isn't quite right. Okay, so I can look at the matrix function for the mapper, and this has a width of 8, and my matrix actually it's got a different layout. It is 32 across and 8 up and down, but it also, if you notice, starts incrementing. It goes over all the pixels, and it sorry, the pixels start by incrementing in the X direction. Well, my pixels actually start incrementing in the Y direction. So the first thing I can do is actually change the layout here by switching X and Y. And you can see the preview. So now you can see that the layout is has swapped X and Y, and the width of my matrix. So even though the width of my matrix is 8, this is now going to be the height. So the matrix is 8 pixels high and 32 across. And what's happening is the Y values are determined, which are now the X values, by dividing by, so each column is the number of pixels in the matrix divided by the width of the matrix. And math.floor just gives you the integer value of that. So each column is going to be labeled 0, 1, 2, 3, 4, etc., because that's 256 divided by 1 divided by, sorry, having a moment here.
Yeah, no worries. It's
no.
It's a little tricky because we've swapped
X
and Y. So width is now height, and Y is X, and X is Y and stuff, right?
But it's right. I've swapped X and Y to I've reversed my example. But yeah, so I've got I'm swapping X and Y because my columns, it runs columns then rows, whereas this example runs rows then columns. So by swapping X and Y, we can do that. So actually, let's just see. So the point of this was to show that you can kind of screw around. Even if you're not quite sure what you're doing, you can actually screw around and figure it out without actually having to know all the math and all the cool stuff. So that was actually my point in doing this. So if we go back, I know I've swapped X and Y, and I know that I've told it that, what was the width is now the height, that is 8, but I think it's not quite right. And we can see, we can kind of test this out by, I'm skipping ahead here, by going to the code editor and creating a new pattern. And you see, if you click on it, this doesn't show you whether it's right or wrong, because you are like, it shows if you create a new pattern in the code editor, it shows you a rainbow by default. And I recognize I'm skipping a little bit far ahead, but just bear with me. I will go back. So if you go to the code editor, the render function is what displays the pixels. And really briefly, you can display a red, green, blue value in the render function by just typing in a red, green, and a blue value. So right now, this should fill the matrix with red. But the way I use this to test the arrangement of my pixels is by putting in an if statement. If x is greater than 0, sorry, 0.5. This will just help tell me if my pixels are arranged the way I think they are. And add an end bracket here. All right, so, and then here, else. RGB 000 gives you a red, blue, and green value of 0, which should be blank. Oh, yep, sorry, render 2D. All right, I've skipped totally ahead in my examples. We're going to go back. I'm going to come back to this in a minute, but yeah. All right, so in 2D space, you can see that I will come back to exactly how I did this. But right now, all I know is that I should be seeing if x is greater than 0.5, it should be lit up. Right now, I can see that my matrix is backwards because my low value pixels are lit up. Right, this is x. From at least my perspective, this is x from 0 to 0.5, and this is x from 0.5 to 1. And I can also take a look at my y values. And I can see on the screen that that the y values run from 0 at the top to 1 at the bottom, which I've also skipped ahead on, and I will go back and explain. So the bottom half of my matrix should be lighting up, but the top half is. So just briefly, if you attempt to map your pixels, and I realize I've skipped ahead to the coding, but we'll get back to that in a moment. If you map your pixels and realize they're wrong, I happen to know that everything's backwards. It's actually a pretty simple fix because I can just make x negative and y negative, and the mapper sorts it all out. You can give whatever coordinates you want to the mapper, and it will actually figure out where they are and then normalize them to, so even though I'm giving this values, if you look from, you know, from 0 to 8 and 0 to 32, it takes the horizontal layout of pixels that runs from 0 to 32, and it will normalize that from 0 to 1, and the horizontal range of pixels from 0 to 8, and normalize that also from 0 to 1. And so all I have to do to flip the orientation of the vertical or horizontal pixels in the matrix is if I make this negative, I'm actually giving values from -8 to 0 and -32 to 0, and it's still going to normalize those to world coordinates. So now I've jumped in a little too fast, so let's go back and make it a little simpler. So, but basically the point I was trying to make is you can play with in real time and see where the pixels are in your physical object. And if it's not quite right, it's actually really easy to tinker with the code to check on it. So let me go back to something that was actually a little bit of a simpler example. So if you look behind me, I'm going to change the viewpoint here to this. If you can see behind me, there is a string art project right there. So the simplest way to use the mapper is to actually just put in data points. So let's go back to that. So here is the code for my string art. If I go to the mapper and delete this code, I can actually just pull up a list of coordinates of each of the pixels in the string art behind me. And as you can see, it's pretty complicated. And I did a little bit of math to figure it out. So when I computed the coordinates, I came up with a file of.
Is everybody seeing the
hang on,
the string? It's really cool. And I
Can you
think
see it behind me? Do you need me to zoom in on that?
I think if you stop presenting for a second, we'll see your video more prominently.
Oh, that's it.
Switch back
Yeah,
to
yeah.
presenting.
Hang on. Yeah, I can also do a. Hang on. Okay, if I, yeah. Let me, here, hang on. Let me zoom in on the, can you guys see the string art behind me over my shoulder here?
I think if you stop presenting, because right now we're seeing mainly, we see you, but it's
yeah,
yeah, there we go.
I did stop presenting. Okay. So the string art behind me is a complicated series of, it's an LED string wrapped around in a regular pattern that's mildly complicated. You're basically just changing by an angle each time you wrap the string. So you can do the math and find all the coordinates, which I did do. I'm going to show you. So I came up with a list of coordinates, and you can just literally enter the coordinates into the mapper as an array with square brackets. So here, if you do this, so the easiest way. Oh, now I got to back to presenting. Yep. Hang on.
Sorry.
Yeah, no, that's all right. There we go. Okay. All right. Can you all see this? So I delete them. Okay. So here's the PixelBlaze mapper tab for the string art behind me. And if I just literally paste, the string art has 100 pixels. And if I just paste the coordinates in an array called map, you can see that it's a bunch of XY coordinates, and it gives the layout of the pixels in the map. Now, if you don't want to do the math to find the positions of all the coordinates, there's a neat little trick. Ben made this great web app that allows you to literally click on a picture, and it will give you the coordinates that you're of whatever you're clicking on. So if you click on all the LEDs, it will tell you where your LEDs are in two-dimensional space. And it doesn't matter if you notice that the coordinates I've given it again are not particularly normalized, and it doesn't matter what they are, because once you enter in all the coordinates, the PixelBlaze code takes it and says, okay, now we're going to normalize everything. We're going to compress it in X and compress it in Y so that the values actually run from 0 to 1 in both dimensions. And oh, Ben, will you drop a link to the mapping, the mapper, the coordinates, I forget what you call it, sorry.
Photo tool, yeah.
Pixel map photo tool. So I'm just going to show you briefly how it works. So what you can do is, if you don't want to do the math to generate the coordinates, you can use this tool. And there we go, thank you. So hang on, so you can go to this, hopefully you guys can, everybody see this? The tool showing up in my share screen? I hope so. So you could select a file with a picture, for example, of what I've done. Here is a picture of, it's kind of a fuzzy picture. It was a very low resolution of the LED string art. So if I had them all, if I plugged it in and just lit them all up, I could then click on the location of each coordinate. And in order, oops, no, that's actually not what I want to do.
You can press Z to
ZZ, yeah, thank you. So you can press on the location of each pixel in order, and what you see it's doing here is it's actually generating a list in exactly the right format you need of coordinates. And again, it doesn't matter what the range of the coordinates is, because once it goes into the mapper, they will be normalized from 0 to 1. So you could actually just copy these and paste these, which I'm not going to do, but it's a neat little tool if you have some sort of irregular pattern that you're not sure. I mean, much of the time you're dealing with strings and matrices, but if you wanted to make some wild artistic pattern, you could quite easily. So the other thing I wanted to point out is that, by the way, when I did this, I also did a little test to see if the X and Y coordinates were in the right orientation, and found that they were backwards. So I ended up taking my pixel map and then making a function of it where I flipped the X and Y coordinates. And I'm just going to copy and paste that in right now, because that's a little fix it all. So if you test things and things don't look right, you can actually change the orientation, which is what I did here. Basically, I put my coordinates in a function. Pixel count is a variable that's automatic to the PixelBlaze ecosystem, the PixelBlaze IDE, and pixel count is whatever the number of pixels you have entered in the settings is, and it's available to your code, and it's available in the mapper and available in the code. All right, so this is kind of a brief overview of the mapper. It takes points, and it takes or it will take a function. You can generate the points from within the function. You can enter points. You can manipulate them afterwards. What I've done here is gone through my points in my LED string art, flip the X and the Y because they were backwards, and return the map, and that all works fine. And if you save it, it's all good. One brief thing I wanted to point out, not there, hang on, there, right there. So if I go back to my LED matrix and save this, and if I look at the patterns, so I have this, let's see, I'll go to blinky eyes, if that should hopefully work. Okay, so
I think your
I'm not
your
sure.
video feed is
yes,
is on
thank you.
YouTube.
Yep. Transition. Hang on one sec. There we go. That's what I wanted. Okay, so yeah, I've selected. Oh, and am I still sharing though? And I need to.
Yep.
Are you able to see the? Are you able to see the PixelBlaze window too?
Yeah.
I'm still sharing. Okay, great. So I created a pattern called blinky eyes. And if you look in the mapper, it's actually, the eyes look basically right. I mean, not great, but basically right. So it shows that my coordinates are at least not totally messed up, but they're working. But the pattern is filling space, and the aspect ratio of this matrix is very horizontal. So you have the option here to do fit. If you look under the preview of your matrix layout, there are two options: there's fill, and then there's contain. And the difference is fill will take the normalized pixel coordinates from the mapper and stretch them to fill, and stretch the pattern to fill that entire space, whereas the contain option will take the largest dimension of your pattern and map that to from 0 to 1, and the smaller dimension will actually be kind of truncated. So if you have a pattern in which the aspect ratio is important, you may want to use contain. Now, it's a global setting, so all your patterns are going to show up that way, depending on how you set it. But it does, if you can see with the eye example, for example, it makes it look dramatically different if you have an LED arrangement where it's not kind of a square-ish aspect ratio. That's, I mean, kind of the, so you can see if I go to fill, my eyes, it actually fits the entire pattern on the screen, but the aspect ratio changes how it looks. So just something, I generally use the fill pattern, but there's a few patterns where contain might actually look better and show the detail you're looking for. I mean, that's just an aesthetic choice that you can use. So I'm going to go back to fill for the examples I'm planning on. All right, so that's the mapper, and I realize I did it a little bit out of order, but assuming you can map the pixels in your arrangement. Any questions about the mapper before I move on to coding? The next step is going to, and just drop it in the chat. The next step is going to be to create patterns. I am not an expert on LED patterns. I'm not an expert, I'm far from an expert on coding. I am an expert at just hacking at things until I get what I want out of them. And that's kind of a really good approach to take when creating your own patterns with PixelBlaze.
So one thing I wanted to point out here is that with once you get a pixel map going for your PixelBlaze and you've configured your LED settings and all that kind of stuff, you can use pretty much any of the patterns that are out there without having to edit the pattern itself. And so if you have a 2D pattern that somebody else wrote, you can just load that in and run it on your PixelBlaze. And those patterns are really a good way to learn how people have done stuff. Sometimes they're very complicated, but there's little bits that you can pick up there, or interesting tricks. And so there's a pattern sharing site where people can upload any PixelBlaze pattern. It's a great place to go find patterns that you want to try out or interesting, or you're looking for ideas or want to know how people code these patterns. There's just a ton of patterns up here for you to look at.
And it's really nice because, a lot of people have really written, oh, here's a Christmas tree, and this is new. This is great. Written some good explanations, and you can actually, before you download it, take a look at the code and see what is available. So I mean, that really is the key to making PixelBlaze easy. It's why I can run the exact same patterns on my necklace as I can on this 2D matrix. And I saw there was a question about if there are any assists for 3D mapping. I can't answer that if there are assists. I can talk a little bit about, I mean, there's a couple of built-in 3D mapping 3D mapping built-in patterns in the matrix. I've got this cube, and if you look in the mapper, it's, there's a built-in kind of cube pattern, which you have to tweak depending on the direction of each of your matrices in the cube. One thing, I was able to adapt the cube. It's actually really pretty useful. It depends how complicated your patterns are. I was able to adapt this built-in cube pattern to work on the surface of a sphere without too much difficulty. And one thing that's really, really nice is the forum that Ben spoke to. You can find it if you go to electromage.com, and instead of selecting patterns, you click forums and ask a question there. I think almost all of you probably came from there or know, but if you have a question about mapping, you're going to get an answer. I've seen a lot of how do I map this questions helped out there. I do know there are I know some of them are some commercial Christmas tree mappers and stuff like that will do we'll do 3D mapping for you. Also, if you can use the mapping tool, depending on how many LEDs you have, if your 3D patterns laid out in 2D, matrices, unless you have a string that's winding all over space in 3 dimensions, you could generally use map each one in 2D and then just add a Z coordinate. But I don't have Ben, there's no assist tool for 3D mapping that.
Yeah, there's no automatic video-based 3D mapping. There's some people have had some luck with some of those tools. And there's some information about that on the forums, but generally most of the 3D stuff that I've seen is uses some sort of pattern that could be expressed in code to generate the pixel coordinates. But yeah, like Deborah said, if if you have like a particular thing that you've built, people have gotten all kinds of help. We've had some really cool 3D map challenges that people really love to help out with that stuff. So it's awesome.
Oh, yeah, and that's a good question, Scott. About disadvantaging NeoPixels versus dot star. Yeah, there's actually Ben has sold me. Actually, Ben is probably the best evangelist for this. Ben has sold me on the dot star or the APA 102s versus the versus NeoPixels. Ben, I'll forward that to you because you'll explain it more succinctly. But
Sure,
yeah,
I could give my pitch.
you do it.
So either works fine with PixelBlaze, but PixelBlaze was really built from the ground up to take advantage of the APA 102 or dot star type LEDs. And those LEDs have an extra 5 bits of brightness control per LED. And very few libraries or LED controllers really take advantage of that. Some of them will let it use it to like change the entire brightness of all LEDs across the entire strip or whatever. But PixelBlaze does it individually. And so you effectively are getting just an incredibly high range of brightness control over your LEDs. And it gives you a high dynamic range. So you can go all the way from the brightest bright to the dimmest dim on the same LED strip. So your gradients and transitions and things like that are just super, super smooth. It just gives you a lot more range. And it's great for anything that you're dialing down a little bit. So if you have a piece, you don't need it to be super, blaring at night. You can really, really dial it down. On the NeoPixel style LEDs, those will go down fairly low, not quite all the way, but then they start to lose their ability to blend colors, and you'll see things like the red is either on or off. It's either red or it's like all of a sudden it's yellow. There's no real blending once you start to really dial it down quite a bit. So there's some advantages there. You could use either. The APA 102s are usually a little bit more expensive. There's less form factors available for them.
Yeah.
But they're, if you have something like that, like a panel or an LED strip, or like the Lux Lavalier uses those kinds of LEDs. It's really great for anything that is wearable, where you're dialing down the brightness. You're not trying to necessarily blind people, but still be able to get color depth. So I'll turn it back to you now.
No. Yeah, that's a better. I totally agree. Like I said, I was kind of agnostic, and I'm like, oh, an extra wire. But yeah, I mean, it used to be that the timing was a big issue with the NeoPixels too. But that's, I mean, most of the like kind of plug and play software, works around that, because the APA 102s have a much. It's not so timing sensitive because they have data and clock lines to feed the patterns to the pixels. But that's generally not an issue. But what I'm going to show now for the coding is this matrix right here that I have out is a NeoPixel, but I actually have a nice big matrix made out of the APA 102s, and maybe I'll run the patterns on both just so we can see the difference. These are good questions, and these are mostly above my pay grade, but Jeff, who is answering the questions, has done a lot of work with all of this. So let me see if I should be addressing. I'm going to go back to I'm going to go start on the basics of coding, I think, unless Ben, you want to jump in for some of these really good, more advanced questions before I get there.
I think I missed.
Okay.
I missed one or two, but thanks, Jeff, for
the neighboring pixels have to be generated in advance. I'm a little confused by the neighboring pixels with Tom's question. He's curious how folks make patterns which rely on knowing the coordinates of neighboring pixels. Aren't the pixels?
Oh yeah. So if you wanted pixel-based stuff, you can absolutely do that, and you do that in your pattern code.
Yeah.
What you do is you just set up an array that could contain all of your pixels, and you do that much like you do in like Arduino or C or some of the other type libraries, either packing them in or creating a two-dimensional array. That's there's a couple of different methods of doing that. And then when it comes time to render out, you just multiply the X value back up to whatever your pixel count is. Of course, for this to really work and keep the pixel to pixel ratio, your pattern has to know how many pixels wide and how many pixels tall your LEDs are. But it still technically could run on something else. So you could run something that's designed, or the pattern is set for 8x8 matrix or whatever. You can run that on a 16x16. It's just going to double all the pixels up.
I think if you're talking about mapping non-rectilinear patterns, I think Garrett Mace did an Excel-based kind of mapper that lets you kind of click on if it's a grid layout, but just not everything is lit, Garrett Mace has some sort of Excel-based pixel mapper that
Yeah,
works for that situation.
that's very similar to the matrix generator examples that are in the pixel mapper stuff. But I think the question was about in pattern code. How do you address specific pixels?
All right, that's above my pay grade right now. All right, I'm going to switch to pattern generation, and I'm also going to switch over to Oh, go ahead.
Actually, so as a sort of segue, so there's different ways of coding pixels and LEDs, and there's no wrong way to do it. I mean, you could do it however you want. But one thing I want to point out is, like, for example, your eye animation could quite easily have been done if it were just some bitmaps and you're just turning a specific pixel on and off. But there's a different way of doing it with some slightly more advanced techniques using math that can generate a pattern that has basically infinite depth, infinite resolution that could be used on any size matrix, could be zoomed in on and contain that same information. So you've switched to a heart pattern here, and this is not a bitmap that you're scaling up and down. How does the heart work?
Okay, well, that's okay. This was I'm switching to my this is my example. This is code I wrote. And I'm not sure if it's a demonstration. I mean, the algorithm is not in the pixel map. The algorithm is in the mapper. And I was not going to start with this because this is like a more advanced thing, but I'll certainly show how it works. Hang on, patterns, beating heart. So I'm going to back up and start with the basics of how I got here, because this is a much more advanced example. But basically, it's code to generate the mapper code. Again, jumping ahead that to the editor and all the missing out on all the really neat features of it. But there's some variables here that represent the value that the values that feed into the algorithm to generate the heart. So delta is, you can see that I was going to address this in a little bit in a much simpler way. The edges of the heart are anti-aliased. So this is the distance in everything's in normalized coordinates running from 0 to 1. I didn't want the heart to fill the screen, so the height of the heart is limited to 0.8, out of 1. And these are algorithmic elements that can change, but go into the generation of where are the parts of the heart in world space. So to determine this position of the heart, there's and its total appearance, all you need to specify are the distance for anti-aliasing, the height of the heart, the position of its tip, its bottommost tip. And this heart is generated from, just briefly, if you've ever seen this, is a square plus 2 semicircles to form the curved portions of the sides. Once you know the height of the heart, you can center it by creating an offset that's half the empty space on either side. And these are just this is just a little bit of math that comes out of mostly Pythagorean theorem stuff to figure out where vertically, because these sides of the heart are at 45-degree angles, where vertically, where in XY coordinates the pixels are. So I'm skipping way ahead.
I think you've definitely won the heart of everybody that loves math.
Oh, that's really awful.
But from a strategic standpoint, how did you go about creating a heart pattern?
Oh, how did I go from
the top level? Like, how do you think about
from the top
drawing
level,
a heart? How did you break it up into the pieces and think about, like, how do I do the straight bits?
From a strategic level, I broke the I'm like I say, I am getting back to the super simple stuff. From a strategic level, I won't. I wish maybe I can do a draw to screen. I'm not on Zoom. Okay. From a strategic level, I knew that the heart, if I take out the beating, for example, you can just see, let me see if I can, where's the, hang on. If I take out the beating, which happens in before render, where's the
26?
Height. Yeah, height. Thank you. Okay. So if I stop at beating for a second, the heart is just a square with 2 semicircles on the side. That's a really standard way to generate a heart. It's a square rotated 45 degrees. And if you look at the outline of the heart, and if I take away delta, if I set delta, if you look at the hard outline of the heart, you can see that you've got basically it divides most easily into 3 sections. If you're looking for techniques to figure out, first of all, you need to figure out whether a pixel's inside the heart or outside the heart. And I was actually going to get to that in a much simpler way with the demo I'm doing. But and the easiest way to do that is in this region right here, below where the semicircle starts, these are 2 straight lines. So you got to figure out whether your pixel is in the region formed by 2 45-degree lines above this region, but below this inverted point. You're in a region bounded by a semicircle on this side and a semicircle on this side, and then gets a little more complicated at the very top. Again, this isn't high enough resolution to see where the point is, but in this region, you're between 2 semicircles, but they don't connect. So basically, it divides the algorithm looks at the y coordinate of where you are, and says, am I in the bottom region where the 2 lines are straight? Oh, and the first thing it also does is it takes advantage of the fact that this heart is completely symmetric. So you don't need to look, at the bounds at negative. You start with where your height is, and you figure out what the x values need to be between. But it doesn't really matter if you invert the range from 0 to 0.5. For the left half of your world coordinates and the right half of your world coordinates, they're identical. So it right here subtracts the distance from the center of the heart from your x coordinate to take advantage of the symmetry. It looks at, are you in the bottom portion of the heart? If so, you need to know, again, since you only look at half the screen, are you between the center of the world coordinates and this x equals y line? The middle range of the heart looks at, are you between the center of your world coordinates and this semicircle? And the top portion of the heart looks at, are you between, now you can't go to the center because you've got this inverted point here. Are you in range of this semicircle in this part of the screen? Hopefully that's reasonably clear. So it breaks it down to those 3 cases.
Sort of a divide and conquer kind of
dividing approach. Exactly. Where on the screen are you? This is more complicated than kind of most, but it's actually a similar technique I use to the eyes, I think, too. So where are you on the screen? Where do you need to be on the screen? Take advantage of any symmetry you can. And then, you can put in fun, and then if you're near the edges, things always look better with what's called anti-aliasing. You can see here that in a regular grid, a straight line, such as appears on the edge of this heart, it's a little jumpy. So rather than having this hard cutoff between the edge of your heart, what's in the heart and what's not in the heart, you see what's in the heart is bright, what's outside the heart is dark, except unless you're very, very close to the border of the heart, in which case you fade out gradually, and that's what this delta is. And I'm actually going to talk about that in a little more detail in the next section, but that makes things look nicer. And again, I'm not an expert on LED patterns, but my goal in making something look nice it's visually much more appealing if things don't jump around in time. You don't go suddenly bright, suddenly dark, and don't jump around in space. These sharp edge transitions don't look as nice as something that is a smoother, more gradual transition. And a lot of the features that Ben has built into the editor window let you do that very easily. So that's what I wanted to approach at a much simpler, with a much simpler example.
And if anybody is feeling intimidated by this, don't worry. This is a very advanced.
It's not that advanced, but it was like, trust me, it took me a lot of screwing around with math. And then I started doing what I was doing with a mapper. Was like, I had points, I think at some point, like my heart was kind of inverted. And honestly, I know you're supposed to go back and figure out the math. I just kept playing with it till it reverted. So okay.
That's fine.
So, but that's the nice thing about this instant example. I love that you can change the anti-aliasing distance, instantly. It's fantastic, and see, well, that point disappeared. I don't love that. So that's what's nice about figuring out parameters for a parameterized pattern, is you can just try them. Boom, and there they are. So that's my favorite. For somebody like me with a very low instant gratification threshold, it's the perfect tool. All right, so let's get back to something a lot simpler. So I think I want to explain why Ben's tools are so nice for generating patterns, mostly because they let you do these smooth visual transitions in both space and time with minimal work. It's actually not so easy in code to do this because you're used to greater than, less than, things like that. You're not used to a continuum. But so let's look at the tools that make this easy. So all right, so once you have your LEDs mapped, assuming that's the case. This is the grid behind me. Ben, you're still seeing the heart, right? So let's go to the code editor and let's create a new pattern to get rid of all this. So we're going to start super simple. What I want to point out is when you go to the editor and you create new pattern, first of all, you get a preview of what your pattern's doing. Second of all, the things to know about the editor that are important is it starts with two built-in functions, this before render and this render function. Now, an animation is a series of snapshots in time, right? And for each, on an LED matrix or on a set of LEDs, for each snapshot or each frame of the animation you assemble, you need to decide what color, brightness, etc. each LED will be. So an animation is a series of frames in time, and each frame is an assembly of LEDs in space and their colors. So the way you generate an animation is before each frame is generated, there are two built-in functions that show up automatically. There's this before render function, which is called once before each frame is generated. And this is where you do the work. Like, for example, in the heart, the heart changes each frame, but I don't need to recompute the heart for each pixel on the grid. That would be tremendously inefficient use of resources. So any computations that will be the same for the entire frame take place in this before render function. And any functions that take place once per pixel, and I'll take place in this render function, or if you're in 2 dimensions, there's another function which I'll get to. One thing I want to point out in before render, I'm actually just going to get rid of all this right now because I don't want any of this. But one thing I want to point out in this before render function is this delta. For an animation to look smooth, it needs to, the time functionality of the animation needs to be, the frame rate can change depending on how computationally expensive your animation is. And what's really nice about the PixelBlaze is it actually shows you how many frames per second. If you look in the upper right, it tells you how much, it gives you a lot of information about what you're doing. So you can see how many frames per second you're getting for the animation you're generating. And you'll see as the animations get more complicated, this rate will drop. But that also changes the frequency with which each frame is computed. And that's a problem if you weren't paying attention to how much time has passed since you computed the last frame. So this delta, you don't often need to use it because there's other tools to work around it, but this delta gives you information about how much time has passed since the last frame was computed. So say you were modeling something in real life and wanted it to look kind of realistic, you'd know that over a certain amount of time, like I'm modeling a bird flying, and it's likely to have moved that distance in this time. So you can use this delta function to say between these 2 frames, this thing is likely to have moved this much. However, you don't need to do that because there's other functions that will help you. And I'll get to those in a moment. This render function is called once per pixel in your pattern. And it expects a return value that is a color. And there's 2 ways to generate the color. There's RGB space, red, green, blue space. And all you do is there's a function called RGB, which takes 3 inputs, a red value, a green value, and a blue value. So you could give it red of 0.5, blue of 0, green of 0, RGB, green of 0, blue of 0, and you filled your screen with red. You don't even need to. I don't know why you don't have to type return. Was there like a reason for that? I'm always a little confused by that.
It's not a return function. It's set by calling one of the color space functions.
Okay. Oh, it literally sets. Oh, it sets it at that time. So if you called it again after that, it takes the last one. Okay, great. It's not a return value. It's a call in the function space. Excellent. And you can change. I'm going to assume most people have a little familiarity with red, green, blue. So if you combine red, they're the fundamental colors that mix. So if you combine red and green, for example, famously with light, you get yellow. And that shows up here. And you can change the mix by changing the intensity. My favorite is, green and blue make cyan. Oops. So, and you can change like 0.5. So that's not very interesting in and of itself. It's a little more interesting if you change, some of the pixels to be different than their neighbors. So again, in each frame, you want to look at now where in space your pixels are. I was going to start with an example. Let me briefly switch over to the one before I switch to 2D. So I'm going to briefly switch over and just show the very basics on this LED strip. And then I'm going to switch to a 2D model. So I'm plugging in the LED strip. One moment. I'm putting the power in the LED strip. Okay, so hang on. Let me get over to, and let me switch the project cam. All right. All right, so you guys can see the LED strip right here. So this is, oh, wait a second. Why is there? Oh, this is the mapper. I'm going to take, this is the LED strip. So there is no actual map. It's just a series of pixels. If I go to the patterns, I'm going to click on, by the way, if you want to learn this stuff and learn it well, I actually can't recommend strongly enough reading the comments in a few of the introductory patterns. In particular, I think I've deleted a lot of these from this because for the space. But an intro to PixelBlaze code, I think, was written by Jeff Viduna, as Ben said, and it's wonderful. And you can learn a lot from reading it. I'm going to give you the TLDR, don't want to read, but here's how it looks when you try it version. So if you go into an intro to PixelBlaze code, it actually gives you, it's actually a tutorial you can actually walk through and try out yourself to generate patterns on this strip. So the one thing I wanted to show, I recommend going through it and trying it out yourself. One thing I want to show by generating a new pattern, so I'm going to delete all this and delete this. Okay, so right now nothing's showing. Again, remember, an animation is a series of frames in time. So in the render function is where you determine the color of the pixels in each frame. So it takes a single parameter called index, and the value of index is where is the numerical index of the pixel on the strip, and I think this was 1/6, and that's again that can run from 1 to the number of pixels in your strip. I've just gone back to the settings because I switched this same PixelBlaze from the matrix to the strip. And if I go back to the editor now, so I can say if index equals I don't know, 25. Let's make it red. RGB 0. Let's say 1 0 0 and
You need the else in there.
I guess I do. Yep. Hold on. Else, if it's RGB 0 0 0. So RGB 0 0 0 has 0 values for red, green, and blue. Yep. So if you guys can, it's out of frame. Yep, there we go. Little too zoomed, but you can see pixel number 25. The index is just literally once per there's one number for each pixel on the strip, so you can change which one's lit up at any time. So the index is where you are in space, and that's great, but it's not going to be very interesting. It's not an animation if it's not moving in time. So the interesting thing comes when you bring in the time functions, and you can learn a lot about the time functions, the time dependent functions, by reading again an intro to PixelBlaze code. And you can also strongly recommend, there's this in the editor window, just literally scroll down, and there's an explanation for everything. So, and if you can't remember anything, it's all the functions that you will need are written down here, including like math functions, built-in constants, very useful for doing computations. And the ones that are most interesting in making things change in time are these waveform functions: time, wave, square, and triangle. And I just want to show you. So for example, the time function. In this before render function, any variables you create will be accessible within the render function to calculate for that frame. So I'm going to create a variable called t1 equals the time function. And time takes a parameter, which it basically multiplies by 6553, whatever. Basically, if time is 0, it creates a value that it returns a value that ranges from 0 to 1 over the time period specified. I think if you put in 0.15, that time period is about 1 second. Is that correct?
It's 0.15, I think.
Oh, 0.15. Thank you. 0.15. So, for example, so how is this useful? So, for example, I could say, to make things change in time, I know this time value is going to go from 0 to 1 over the period of 1 second. So rather than having a fixed index, I could say if index of the pixel I want to light up is equal to, I'm going to round it because this is going to give me a floating point value. The time constant times, so I'm going to do floor time constant times. Now there's a built-in, I think I mentioned this earlier, there's a built-in parameter called pixel count, which is available from the mapper and the editor that references how many pixels are in your string. So now what's happened is we've made the pixel move in time, and it's moving pretty fast. So it's going over so since this time value goes from 0 to 1 over the course of a second, if we multiply that times the number of pixels, it's going to go from 1 to 168 every 1 second. And you can see that it's making the single pixel light up. And now to make it more interesting, so that's a single pixel lighting up. You could do you could make it a clump of pixels by saying if the difference between this value and the index of our pixel is less than a certain amount, then you have a range of pixels lighting up. So if the absolute value of the index minus absolute value just tells you the distance, how far away they are, minus this multiplicative function that gives you an index that goes from 0 to the number of pixels is less than, so I can make it 4, for example. Suddenly it's wider, or you could do 6. And so now we've got things moving. Now it's already more interesting. And now we could do something like I talked about, but it's, still not that exciting. And this is just a blob of pixels moving down the strip. It will look a little bit more interesting if the edges aren't as bright, so it's not as sharp a transition. I'm still going to slow it down by just literally raising this time value. Okay. And now it's moving about 3 times as slow. But it's still just kind of a blob. So you can fuzz out the ends of this blob moving down the strip by instead of having this RGB value where it's full on the maximum value of red, no green, no blue, you can say that you could make the red component vary with distance from this moving point, this point that moves down the strips. So you could say, all right, I'm going to have this distance d between this point that's moving down the strip, and that's going to equal the absolute value of the index of my pixel minus position of the point moving down the strip. And then you could say if the distance is less than 6, the RGB value is going to be brightest towards the center. So it's going to be 1 towards the center, but the further away we got, the more it's going to drop off. So it's going to be 1 at the center, and we're going to subtract the distance, distance divided by the width we want. I should probably just make that a variable rather than 6. I don't know if you can see it. It's probably not showing up as well on on this one LED strip with this one camera, but we'll see it again, and we'll see it a little more clearly in 2D. But what we're doing here, and I've got a mistake here, T1. What we're doing here is kind of softening, anti-aliasing the edges in one dimension. And it'll be more clear in 2 dimensions when we do this. So what I'm doing is basically creating a gradient towards the end of the pixel, and it makes it look smoother and nicer. So this is all fun and good. And I think that the other time functions are a little more easy to understand when you look at them in 2 dimensions. So I'm going to switch over to the LED matrix and demonstrate some of them now. Any questions so far? This has been a really pretty simple intro, but what you can do with these time functions and the ones that depend on it are really, really interesting. And we'll go to 2D to really look at them. So I'm going to switch to that and to my matrix. Okay, so analogous to what we did in the LED strip, I'm going to create a time function. So this render function assumes doesn't know about your position in space. So if you're in the editor and you want to make your animation depend on your position in space in a two-dimensional pixel layout, you don't want to use the render function because that only knows where your pixel is, the index of your pixel on the strip. You have to create, and I think this is down here somewhere. You can read about this somewhere in the information here. Create a function that renders your frame in 2 dimensions. So it's similar to the render function. And oops, sorry, is it cap? Oh shoot, now of course 2D. And it takes as its arguments, it still gets the index of the pixel, also the X and the Y value stored in the mapper. Okay, and so now what we can do is we could make it, do what we did before. It doesn't matter, independent of position, just give it a 0, 0, 1, just give it a, just make it all blue. But we can also make it vary in time and position. So we talked about this function, this time function, T1 equals time, you give it some value, 0.5.
So one thing I just wanted to point out real quick was you have a render and a render 2D, and so PixelBlaze is going to automatically pick the one that's most appropriate. You can tell which one it's using. If you look up on the top left of that live preview bar, there's a little 2D in a square up there.
That's right. Yes, exactly right. It will always drop that, right? Render works on any pixel layout because every layout has an index. If I were to delete this and not have a render 2D, it would get very confused. It will always be able to use it drops to, the most appropriate render function. It knows how many dimensions it has from the mapper tab. Okay, so now I'm going to use this wave function. And I'm actually going to, so it explains what they are down here. So T is a time varying function. Wave is basically like a sine wave function, except it works in normalized coordinates in both space and time. So whereas a sine function has a range of 0 to 2 pi, the input to this wave function runs from 0 to 1, and the output runs from 0 to 1, rather than -1 to 1 as a typical sine function. I think Ben's done some explanation of that down here, but let me show you how it works. The easiest way to do it is I'm going to use the wave function to vary something in space but not time, and you can see how it looks pretty nicely. So I'm going to have distance. I'm going to create this variable distance equals. I'm going to create a 2D graph basically. So X is the independent variable, Y is the dependent variable. So distance is equal to the dependent variable minus this function I want to map, which is the wave function of X. And then, okay, display it. I'm going to have if D is less than 0.1. So if we're in this range, RGB 1, 0, 0. Okay. Oh, whoops, I didn't mean quite to do that. Okay, I did it. So you can kind of see, I meant to actually do an absolute value. I wanted the distance. Not, I didn't want that to be negative. Okay. So a wave function remember the parameters of this space are 0 to 1 in x and 0 to 1 in y, and y runs from 0 at the top to 1 at the bottom. So you've got this wave function that varies smoothly. You can also look at a triangle function. There's also a built-in triangle function. And there's also a built-in square function that has a duty cycle. So you can do square. And a duty cycle just means how much of the time a square function returns 0 or 1. And the duty cycle tells you for how much of that period is it 0 and how much of that cycle is it 1. Now, and what's nice about these functions and the way, not so much this, I'm going to focus mostly on wave because that's the way to make things look really nice and smooth. What's nice about these functions is that they repeat. So if you're creating an animation, like this is a wave, but say you want it denser, you just increase the frequency of your wave. So right now, this wave function again goes from 0 to 1, and x goes from 0 to 1. So you've got one entire wave cycle in your frame. But all you have to do is increase the frequency. So say you double it. Suddenly you've doubled the density of that pattern, basically. It now goes over 2 complete cycles in the x space. Now, again, this is not an animation because it's not moving in time. So the way to make things move in time is to add a time component. So I've got this wave function now. And all I have to do is take the position. Because it repeats, it doesn't matter how big the argument to wave gets. So if this is moving a little, I want to make this move a little faster. So I'm going to make this smaller. So now we've got our wave moving in time. And it's starting to look a little more interesting. That's an animation. It's even more interesting if I'm going to do the anti-aliasing thing, which right now, it's only going to draw a pixel if the distance from this function generated by the wave is less than 0.1. I'm going to actually make that a global variable. I'm going to call this my line thickness right here, and I'm going to create a variable at the top. 0.1, just to keep it clear. So if d is less than, okay, so right now you've got this. But instead of doing that, you can, I could just, instead of actually, if d is less than, sorry, how was give me 1 second to look at my notes. I don't want to get too far off. Yeah. Okay. Rather than have it drop off suddenly, I'm going to make this a little thicker. Rather than having it drop off suddenly, we can make, actually I'm going to switch from RGB space to hue saturation value space, which I haven't talked about right now. Now, up to this point, I've only generated colors for the animation using this RGB function, which takes, a red value, green value, blue value, but it's a little tricky. What's tricky about RGB is how do you, okay, say I wanted a little, you can specify how much of the components are in each color, but transitioning from color to color can be very tricky in RGB space because how do I take this color but make it a little dimmer? I guess then you make each component just a little bit dimmer, but then you've got 3 components to mess with if you want to make it brighter or dimmer or less intense or more intense. So if you want to fine tune, if you're not so worried about changing colors, but you want more fine control over intensity and brightness, there's a different color function you can access called HSV, which is hue saturation value. All 3 arguments run from 0 to 1. The first one gives you a hue. So 0 is red, I think, and it loops back around to red. It's continuous, which is nice. The saturation is the second point of saturation is how intense is the color it's generating, and the value is the brightness. So let's give that to 1. So now we've got this red sine wave moving because we've specified the color here, the hue, the saturation is 1, and the brightness is 1. So you can see it's really simple to just change the color. Now I just got a 0.2. It's a rainbow, or I could make the color change with time by just switching to this function that runs from 0 to 1 in time, and it's going to be a smooth transition because it loops Again, so the key is by using this time function, I don't have to worry about, what happens when I get to the end, how to get back to where I was, because time, because the hue loops again when you get to 1 after it goes back to the value I had at 0. Okay, so you can also just briefly, if you want to see the saturation, if you turn the saturation down, the colors are going to look more muted. I generally, which is a neat effect, I don't tend not to use that much, but there are some really cool patterns that depend on that. The nice way to implement smoother edges or anti-aliasing is using this value or brightness component. So I can make, instead of 1, which is, I can subtract a little bit of brightness the further away we are from the center of this wave pattern, which I did before. So D is the distance from the center of the wave pattern, and I want the most I want to subtract from the brightness is 1. So if I subtract the distance divided by the thickness, it's going to be a lot smoother and produce a smoother pattern. And I'm going to make this a little bigger. The thickness, we'll make it a little thicker to show. So suddenly now we've got a nice smoothly moving animation using this wave function right here. Let's see, where was I going next? Any questions so far? Okay, so one other thing I want to show you, just to keep in mind. So again, you could change this to triangle really easily. Suddenly you've got sawtooth. You could change the frequency, some by not multiplying x. You can change the speed by changing time. You can also, right now this pattern's filling the screen. You could create an amplitude.
Yeah, that's actually a really good visualization of these different waveforms.
I find this a lot easier to visualize in 2D. I hope people understand. So, the trick is then putting it back to 1D. Yeah, go ahead.
So if you delete the keyword triangle, you'll get just the sawtooth that's generated by the time function, which
you delete sorry, which keyword?
On line 12, if you can leave the parentheses, just delete triangle. Yeah.
Yep. Yes.
So this is, it may be multiply x a little bit because it's going out of frame. Yeah. So this is.
Hang on. Wait,
it's not modding. Never mind. Never mind.
Yeah, I'm gonna get. Actually, I think I'm gonna get to something that uses the point you're talking about. But yeah, it's right. The time function, because you to visualize the time function. Yeah, you're just trying to visualize the time function.
Yeah, it's like a slow ramp up and then a sharp drop back to 0.
Yeah, I was going to show that too. Here, I can show that in a minute. So here, I'll show it this way. So hang on. So right now I've got this wave. And I'll show how that works. So let's create an amplitude parameter. So right now the pattern we've generated fills the screen. But we can create an amplitude equals, say I don't want to fill the screen. This is kind of what I did with the heart. Let's make it 0.6 of the screen. And to do that, remember, here, I'm actually going to create another line of code and take this out. So I'm going to create value. The y value at any particular position of x is generated by this function right here. So let's take it out. So x minus value, and this is how far we are from the y value. So the brightest pixels will be at the center of this function right here. If we multiply it by an amplitude, our wave by an amplitude. Okay, so now, all right, so this is cool. We've moved our wave in space. And we can actually, but now it's running from 0 to 0.6. It'd look nicer if it were centered. We can also give it an offset equals, so I know that my wave, again, this wave function goes from 0 to 1. The amplitude is 0.6. So I want to move this to have half the empty space on top and half the empty space below it. So we're going to create an offset that's 1, the height of the screen minus the amplitude, divided by 2. And then I'm going to add the offset to the function. All right. So now it's more centered. But now, so here's what I'm going to show what Ben was referring to. And so this is fine. It's like, why am I bothering with this? Well, you start to get more interesting when you make the amplitude of the wave vary in time. So I can create another time constant for example, T2 equals, I'm going to make this one a faster, right now, this time constant is how quickly the wave pattern's moving across the screen. I'm going to make a time, make one that's a little faster, 0.002, 0.02. And I'm going to make the, actually, sorry, I'm going to make the amplitude, I'm going to make the amplitude a function of time. And what you're going to see is exactly what Ben said, by the way. So what's happening is the amplitude's changing suddenly. You can see how this time function is causing the amplitude to grow and grow and grow and then drop back to 0. Is that, hopefully that's a clear example of how the time function works.
So time's going from 0 all the way to 1, but then you're multiplying it again by the 0.6. So it's going from 0 to 0.6, basically.
Yes. And you can make it so, again, you start to make more interesting, when you start to want to play with things, things become more interesting and smoother. So instead of doing time, which is going to make the height of this kind of like sharp and jaggedy and not such a cool, I mean, if that's the effect you're going for, great. But if you want a smooth, more interesting animation, then you just put that time inside a wave. And suddenly the amplitude modulates itself, smoothly. And that becomes more fun. And then you can start to do things. And I'm going to start, and then you can, so right now, I'm using 2 dimensions to explain concepts you can apply in 1 dimension, but things become even more interesting when you start to use these wave functions in 2 dimensions. Right now, everything's scrolling in the x direction and all the interesting stuff is happening in the y direction. So let's create, if there are no questions about this, let's create an interesting animation where things move in an interesting way in more than 1 dimension at a time. All right. Again, some of you, this is going to be really low level stuff for, and I apologize, but I think in my mind, these are the basics of making things interesting, is smooth transitions and how you accomplish them with the functions that are given here. Also, one thing to note, by the way, well, I'll show in a second. So, okay, so let's do something different. I'm going to create a new pattern. I'm going to delete this one. Okay, so we don't need our render. It doesn't matter about this render function because I'm going to create a render 2D function. 2D index x, y. And what I'm going to do is I'm going to create what did I do? Oh, export. What I'm going to do, what did I do?
The function keyword.
Function, oh, yep, thank you. I'm going to create a ball bouncing around the screen. But I'm going to make it bounce in an interesting way. We're going to have both. So the ball's going to have an x and y position that we're going to map. And so here, so let's do, so in before render, our ball is going to have an x coordinate and a y coordinate, and I'm going to make it a red ball. So I'm going to call its x coordinate xr, and we're going to make it, its x position vary like a wave. With the time period, I don't know, 0.03, for example. And the y coordinate of this red ball is a wave function with a time period. I'll show you what happens when you do 0.03. So let's do same x and y coordinates. So what's going to happen is the x and y coordinates of this ball we have are going to vary this red ball are going to vary between 0 and 1 with the same time function. So the way to draw the ball is to determine, this is a much simpler version of what we did the heart. For every pixel, so remember this before render function gets called once per frame, because in each frame, the ball is going to be in the same place. So we only need to compute the position of the ball once per frame. And within each frame, we need to know, is each pixel inside the ball or outside the ball? So the distance for each pixel, I'm going to call it d, of any pixel x and y is, if you guys remember, there's this nice little built-in function that will do this for you called hypotenuse, and you can look up what it does right here. But if you scroll down to the functions Ben's made available, it tells you the distance. It's basically the Pythagorean theorem in function form, and I'll let you look that up. But it's hypot, and I'm going to take the distance minus xr y minus yr. So it's the net distance of x and y from this point xr, yr is given by this function. Oh, and it's not liking this. I'm just going to delete that. Okay, and then we're going to say if D is, let's create a radius for this ball, and I'm going to put it inside this before render function because we may make it vary later. So radius, let's do radius R. Red ball is I don't know, 0.4, 0.3. Okay. If the distance from a point to the center of the ball is less than the radius of the ball, right? R will we'll do HSV. We'll make it actually. This is the trick I want to do. So we're going to actually use our RGB values here. So I'm going to say R equals 0, G 0. These are going to be the red, green, and blue values to generate the color of our pixel. They're all going to be 0 unless our pixel is inside the ball, in which case the intensity is going to be brightest at the center. So when the D is the smallest, the intensity will be, the R value will be the brightest. So the R value is equal to 1 minus the distance from the center, scaled from 0 to 1. So minus D over red R. And then after we've done a little computation, we'll have R, RGB. Okay, now we've got this ball moving around. By the way, you can see if I, okay, so you see a ball with nice anti-aliased edges. Now it's bouncing from corner to corner. And the point of that, and that's because most of you probably know this, but again, remember I'm used to teaching kids, so I'd like to show what happens when you do something like, and have people catch the mistakes and tell me. It goes over big with the kids. So when the time period of the X and Y oscillations are exactly the same, it's going to repeat. The X motion and the Y motion are going to repeat exactly the same. And that's not very interesting. To make it this motion more interesting, if we give it a different period, that's kind of cool. But also notice what I've done is I've made the time period of the X and Y motion. I've made the Y motion slower by a factor of 2. Sorry, by a factor of 20. Is that right? By 20? Yeah, I guess that's what I've done. Wait, no, by 5. Sorry, Jesus, 5. Here. And it's still going to repeat the same pattern over and over again. So if you're trying to create a pattern, which is fine if you want your pattern, but so this pattern is going to basically, every 5 cycles in X, it's going to end up at the same position in Y, basically. And so that pattern is going to repeat every, however many times a second Y repeats. So animations look more interesting if you have multiple things oscillating. They repeat less often if the time constants, if the time scales over which they repeat are not multiples of each other. So to make it more interesting, it's really nice. Like if you use what's the word I'm looking for? Prime value, kind of values that won't have common divisors, like prime values, that you start to have like more interesting motion, for example. So I'm going to make this a little faster too, but so this is like a more interesting looking kind of motion because we've made the time constants not multiples of each other. So, and again, I'm just making a ball bouncer on the screen, but it's actually a decent principle if you want kind of patterns that look like they're infinitely varying. If the time, if they repeat over a certain time period and those time periods have common factors, you're going to have a repeating pattern once those once the multiples match up again. All right, so this is the basis of an example I was going to do, and I was so because it shows anti-aliasing, it shows motion in 2 dimensions, and the trick to making it kind of interesting now is you can make the radius, for example, expand and contract. So rather than having the radius of the ball fixed in time, you could multiply it by wave time, and then like another. You can make it kind of slowly grow and shrink. So I don't want it to go to 0. So right now the radius oscillates between 0 and 0.3, but I'm going to add a constant. So it's going to oscillate between kind of half the size of the screen and the full screen. And this was like my last example. So I think for most of you, this is probably a pretty basic example, but if you repeat this now, so now I've got one ball bouncing around the edges of the screen, somewhat unpredictably, a little bit quick. You can do a similar thing. You can add another ball make it, say, a green one. And obviously you want to give it different time constants. And green ball. And I don't know, just pick a 37. And then calculate the distance. So now we have to check to see if our pixel's inside the red or the green ball. Calculate the distance. So I'm going to call this distance to the red ball. And do the same with distance to the green ball, using, again, this distance function. Minus xg y minus. To determine if the pixel's in the green circle. And if it is, I don't think I specified it. There. Make the radius of the g equal 0.2 and point. So we're creating another oscillating radius for the green ball, and that radius is in the variable rate g. Then the green value is going to be 1 at the center of the green circle. And see, right now, not anti-aliasing. So right now, I don't like that radius is way too big. 0.1. I will leave that for now. And they're moving a little fast. But here. So what I would do, by the way, these are moving really, really fast right now, and I don't love that, how quick that looks. So one way to fix that is to create a global variable called speed. Speed equals 1. And you can have your time constants vary by this speed function. So
I think you want to end the time function.
I do want to end the time function. You're right.
Yeah.
Yep. So now, wait, hang on. These will all scale together. So if I want to speed it up, I've actually, so speed equals 1.5. Oh, whoops, wrong way. Okay, I've got speed going backwards. It should have been multiplicative, huh?
Maybe just put in a small number.
Yeah, okay, well, yeah, right now speed increases, yeah. All right, hang on. So, sorry, no, that's my fault. I put it in the wrong. Yeah, I didn't mean to put it in here. Sorry, that's the radius. I meant to put it in the position. That's all. Okay. There we go. That's, yeah. Okay. That's what I want to do. Okay, that makes more sense. So that slows everything down on kind of a global scale. So I'm basically scaling all the time factors by the same amount. And you can see, by the way, you can see the difference that it makes, the drop off of the saturation around the edges. So so instead of having this green value, go from 1 to 0, we'll again subtract it slowly by using the distance, by subtracting the distance over the radius of the green ball. And now you can see when the balls actually overlap, you're going to get yellow. And it's kind of a neat looking pattern. And you can extend this concept, by making colors and hues very smoothly. Right now, the condition for the pixel is distance from the center of the ball, but you can do it, you can use all kinds of kind of organic looking fields, like to create functions that vary interestingly over time. Right now, I've just have balls that move in space according to simple wave functions, and you can put in the blue. But that was basically kind of the extent of my example for creating simple animations. To summarize, the important points I wanted to make about making things interesting is you want possible smooth transitions, taking advantage of these wave functions. Oh, one more thing I did want to show. Well, I don't know if it's.
I just want to do
go ahead.
Time check. We're about where we wanted to be.
Yeah, I'm basically done with the kind of the points I wanted to make. I wanted to show briefly HSV drop off, but I suspect most of the people in the chat actually know it. So I'm going to stop here. Like this, you could see how you can extend this example to have like a blue ball bouncing around too, which is what I had, I think, in my final example. If I go back here, where was that? I had, listen to, I think that was it. I had like red, green, blue bouncing around. And that was it. So yeah, those are the basics on how you apply them. And you could say it really does apply in one dimension too. You could take this pattern and make it display on a 1D strip by just modifying it slightly. By saying, you could pretend your strip runs across the middle here and wherever these blobs intersect it. So I can even try that really quickly, for example. Let's do that.
We could do the same kind of thing, just just ignoring Y.
Exactly.
Using X across the strip.
Yes.
I do want to wrap it up and let folks go. I know people have their Saturdays to get to, and I just want to thank you so much for doing this workshop. It's been amazing. I hope everybody's gotten everything that they were looking for out of it, and look forward to following up with everybody with additional questions. Please hit us up on the forums. Happy to answer that. And I had offered to do sort of like an artistic sort of like, how do you use all this math and expression stuff to just kind of create stuff without even like mathing it out and knowing what's what. So I hope to follow with folks there. If anybody has some quick last minute questions, answers, or praise for Debra, please
questions, please
toss it in the comments here. And while people are typing that out, Debra, do you have anything you want to wrap up or close with?
No, I not particularly, other than like, I hope you see the point is really to experiment, and there are a lot of people who've put a lot of work into making great tutorials, including Ben, and again, Jeff Baduna. If you work your way through the examples shown in the, like if you look at the intro to PixelBlaze and the ones that are labeled kind of example code, and really look at the comments, you can learn a lot. And literally just, and you'll see whatever changes you make happen instantly. And I strongly recommend trying that out yourself, because it is the easiest way to learn, is to do it yourself and see what happens. And you'll find, and you learn a lot from like going, wait, I didn't expect that to happen, and whoa, what's going on? Which is a lot of the way I learn. So no, and thank you to Ben for making such an amazing platform and being so responsive to user input. I think many of you came from the forums, but if you haven't checked out the PixelBlaze forums, you should. It's a font of information and really active, helpful, generous community, which is really nice when you're learning something new. So there's a lot of resources involved, a lot of resources available for getting started that are worth taking advantage of. I mean, no matter your level, you can come in with a newbie question and people are really happy to help. That's it. Thanks, Ben.
Awesome. Thank you so much for doing the workshop. It was awesome.
Oh,
I learned a few things. I love your tricks for anti-aliasing. That's good stuff.
Oh, that's your trick. I mean, no, I'm not.
No, that's not my trick. I learned that today, genuinely.
Really? Oh, that's funny. I thought I was taking what you're doing and just simplifying and dumbing it down. Okay, I'm pretty sure that was I think that's what you're doing at a higher level, but
you're smartening it up. That's for sure.
No. Anyway, the goal is to make it intuitive, and if it's not intuitive, you play with it till you figure out what happens over in time. Anyway, thank you guys for showing up and listening. I appreciate it.
Yeah, and like always, there's no wrong way to blink an LED. There's no wrong way.
Nope. Just go out and be blinky. That's all that matters. That's really the thing.
All right, so I will try to get this recording and post that up so that people that missed can watch in. And thank you all for joining, and I look forward to catching up with you all on the forums and Mastodon. And do you want to give a quick shout out for how people could get in touch with you?
Sure. I'll put my Mastodon link in the chat. I technically have a Twitter account, but it's not. I'm on mastodon.social, and I have to figure out how that. How does one? Yeah, I'll put that in the chat. You can follow me there, and Ben, you should do the same. But honestly, the best resource is the PixelBlaze forums. Did that? Not good. Okay.
You can find.
Let's see.
Wizard account there.
Is it? Oh, it is going to, oh, sorry, okay, I didn't see, yeah, sorry, I dropped it in twice. Okay, yes, and there's wizard.
For all things PixelBlaze.
All right. Thank you
Something
guys for
like-
showing up. And thanks for the people I built all this information on. Jeff was really, I was maybe a little late in getting organized. He offered a tremendous amount of help, and he's responsible, I understand, for a lot of the tutorials that are out there, and they're very good, and they're very detailed. So I recommend diving in.
Very good stuff. Very good stuff.
So
yes, thank you all. All right. Well, we'll see you next time.
yeah, it'll get more advanced. They'll turn it up. The experts will weigh in, including many of you could probably come in and teach.
All right. Stop recording.